Hello everyone, I hope you are doing well. In this video, we are going to solve problem 9 from chapter 1 of solid state physics by Wahab. The chapter name is atoms in crystals. Let's see the problem statement and then start the solution as quickly as possible. The density of the statement is the density of BCC iron is 7.9 multiplied by 10 to the power 3 kg per meter cube. So there are two things that are given here. The first one is that it is BCC, okay, iron. It has density. The atomic weight is 56. Atomic weight is given as well. Calculate the size of the unit cell. Okay, we need to calculate the size of the unit cell, and here the unit cell is cubic, okay, in structure, as BCC is given. BCC means body centered cubic. It's cubic, okay. It's already given, so we need to use this information to find out the size of the unit cell, which is the lattice parameter, actually A. Okay, we need to calculate the lattice parameter A. That gives us the size of the unit cell. Let's write the data first, and we'll then go to the solution and calculation. We are given with density of iron is given to be 7.9 multiplied by 10 to the power 3 kg per meter cube. It's in SI unit, so that's good. Atomic weight is given. We will represent it by capital M. It is 57, and atomic weights are calculated in units of grams per mole. Okay, we need to convert it into SI unit, which is kg per mole. We know that gram is not SI but kg is, so we need to convert into it into kg before inserting it into the formula. So in data section, we convert all of the data into SI unit to make sure that in inserting the values we may not find any difficulty. So to make kg, what I am doing is to multiply by 10 to the power minus 3 as well as 10 to the power plus 3, so that it is mathematically consistent. And now we know that k means kilo, okay, and it's 10 to the power 3 numerically. We'll write k in place of 10 to the power 3 here, so that we have kg per mole now, okay. And this is the molar mass. Molar mass is atomic weight in other words, okay. So we have converted it into SI units. Besides that, we need to calculate the size of the unit cell, okay, and we are given with BCC iron, okay. This information is given. That should be kept in mind, because in finding in the formula that we will be using, there will be use of a quantity named as number of atoms per unit cell. In BCC, there are 2 number of atoms per unit cells, okay. In FCC, face centered cubic, there are 4 atoms per unit cell, and in simple cubic there is 1 atom per unit cell. So this is a information that is derived from the type of structure the element has. So for BCC iron, capital N will be taken as 2, okay. So solution, how it is 2, that's irrelevant at the moment. It's a part of conceptual video, okay. So I'll try my best to upload a video where we'll discuss about simple cubic, FCC, face centered cubic, and body centered cubic structures of atoms. We'll study various parameters in them. For example, number of atoms per unit cell, nearest neighbor distance, interplanar spacing, etc, etc. So we can discuss all of those things in that video. It will be coming in the future. I'll link it here if it's uploaded at that time you are watching. So solution is, we know that the density is given by, density of unit cell is given by mass of unit cell, total mass of unit cell, divided by the volume of the unit cell, since it's cubic, okay. So it's a cube in the denominator, volume of unit cell. Cubic structures have volume equals to a dot a dot a, since all of the lengths are equal, so it's a cube Mass of the unit cell is equals to capital N, which is the number of atoms per unit cell, multiplied by the mass of each atom, okay, making up the unit cell. Here atom is iron, so molecular weight is given. Molecular weights, which is atomic weight, okay, atomic weight and masses are not same. You can see the units as well. It's kg per mole. It's the weight per mole of a sample, but we need to find out the mass on its own, okay. So yeah, it's we need to find out A, so I'm just taking A cube right here, and it's capital NM by rho here, and we'll take cube root on both sides so that we are left with A right there. So because it's A cube and we want A only, that is why I took A cube root on both sides, so it's A right here, and it's capital NM by rho to the power 1 by 3. Now keep in mind, what is small m? If it is not capital M, then what it is, how to calculate it. For this, it's always true that the mass of single atom, small m is mass of single atom here, is equals to molar mass divided by Avogadro's number always. Okay, if you want to find out the mass of a single atom, then what we need to do is to divide the atomic weight, molecular weight, or any weight, ionic weight, or what else name is there, by Avogadro's number. You will get the mass of that single unit or single atom or single molecule. Okay, so we'll insert this expression right into here for the final expression that we will use for calculation. Hence it is A equals capital N by rho, and in place of small m we write capital M by NA, and it's to the power 1 by 3. Now let's insert all of these values right into this expression. In place of capital N we write 2, as we saw earlier. In place of capital M we write atomic weight in SI unit, which is this, divided by rho, which is 7.9 multiplied 10 to the power 3. And Avogadro's number, as we all know, it's 6.023 multiplied by 2 to the power 10 to the power 23, positive 23, and is its whole power 1 by 3. Okay, so let me calculate it using the calculator, and then I'll get back to you people. To keep in mind that it's cube root here. Okay, most of the students just get this answer and they just forget about it. Okay, so it's 2.866 multiplied 10 to the power minus 10 meter, or it's enough to write 2.86 angstrom. In place of 10 to the power minus 10 meter, I'm writing angstrom. So this is the size of the unit cell. Okay, and that's the final answer. I hope you got it, and if you have any questions, queries, you can ask me in comment section. If you are looking for some other video that you have not found yet in my channel, then you can simply comment the problem statement. I'll put a link of that video in reply to your question, in reply to your comment, or I'll make that video for you people. And besides that, I have made a playlist for each book, since there are 6 books of solid state physics that I am following, and I have uploaded problems and solutions to all of them. Okay, so you can directly go into the playlist of your desired book, or go to the playlist where there are mixed videos about derivations, conceptual videos, and problems and solutions. So those playlists are named as solid state physics 1 and solid state physics 2. If you are still confused, you can ask me. And goodbye. Subscribe, and share it to other people. That would be a great favor from your side to me. Okay, thank you. Goodbye.